Okay, hello everyone. So I'm Gavin Ferris. I'm the CEO and co-founder of lowRISC CIC. We're a non-profit silicon engineering company based in Cambridge, but also an office in Zurich. And Haydn?
Hi everybody, I'm Haydn Povey. I'm CEO of SCI Semiconductor. We're also based here in Cambridge, although officially for funding purposes in Sheffield.
Thought I recognized the accent. So there's going to be quite a lot of content on the slides. I'm not going to go through, in the interest of time, since I'm also supposed to be facilitating this section. I should set a good example. So we're going to go through, you can see the slides afterwards, they'll all be available. But just pick out some key points on each slide. And let's go. Let's hope I press this clicker in the right direction. Okay, so as we heard in the earlier talks, memory safety is a huge issue. You can take the stats from where you want to take the stats from, but it's somewhere between broadly 50% if you're looking at operational technology type applications, up to 70% if you're looking at IT type applications of cybersecurity vulnerabilities and patches are memory safety related. That's not today. It's really surprising. And cybercrime, not all of it, of course, as Alistair was saying, is dependent upon that. If you lose your password or use bad passwords, something that's not really a memory safety issue. If you abuse things through manipulating people's desire to tell you stuff, sort of social manipulation, that's not memory safety either, but a lot of it is. So a lot of it does base itself on these types of vulnerabilities, and we can and we should address those, but they are still not closed. So in terms of ways that those can be closed, again, three sort of broad canonical approaches. So one approach is memory safe languages like Rust, which we love. Unfortunately, there are a lot of legacy lines of code. And yes, you can point an LLM at that and have it rewrite it, but then are you sure what you've got is what you wanted? Completely sure, and you haven't introduced new things. Secondly, there are formal methods, which again we love, but they are of somewhat limited applicability, and you have to find the right domains to use them. And the third way that you can approach memory safety is through a hardware enforcement mechanism. But those have to be appropriate to the domain that you're using them in. So if you are putting them into an embedded environment, they have to be usable in a methodology and an approach that doesn't require very high overhead. It has to be lightweight. It has to be lightweight in terms of gates, it has to be lightweight in terms of power consumption, and so on, and easy to adopt. So CHERI is a technology, obviously, that we all know and love. We're all here talking about it. We don't need to tell too much more about CHERI, but the interesting thing is how does it get into the embedded environment? And that is, it's good in and of itself, but it's also, because I think, as Haydn was saying just now, we were just doing an interview, part of the marketing, we're pushing that, is that we've seen a lot of people who are going into application task processors, not because they need the power, but because they want to run Linux, because they want to get thread safety through that, which is kind of perverse. Your trusted computing base has gone up. So you really want to keep those lines of code as small as possible, and that means having things available for the microcontroller market. So in that space, we obviously had CHERI. It's come out of University of Cambridge, SRI. Then CHERIoT. So CHERIoT took the zero-RISC core, which came out of ETH Zurich, was made into the IBEX core by lowRISC, which obviously is the foundation of the OpenTitan program, which is the world's most active open source silicon program, and it's gone into commercial availability last year and is now going into Chromebooks and Google servers this year and then later. And they took that and they produced CHERIoT IBEX. Now, CHERIoT IBEX is a co-design. It's the silicon design, so it's IBEX with the CHERI extensions, but it also has an operating system component along with it as well that's been co-designed. So that piece is the first basis. That's how you need to get to market in the operational technology and in the embedded world. You need a core that's of high quality and it's open source, and Microsoft provided that. There are plenty of talks about that. We won't go into that in any detail, but basically IBEX plus CHERI plus an RTOS is CHERIoT, and that is available and has been for some time. So, however, that's just the core. It's sort of floating in a jar. You need to get it into products. So you need to have application engineers able to play with it, and you don't have silicon. So what do you yet? Right. So more on that later. So what do you do? So enter the UKRI and DSbD program called Sunburst, and that had two phases. Right. It's completed obviously at the end of the second phase. Just wrapped up at the end of March. So in the first phase, we aim to get, obviously, things of high quality and improve the verification quality of the core, but also to get an FPGA target that was supported and was usable by people so that they could actually play with it. You could actually change the RTL if you wanted to do it. You could change the firmware if you wanted to do it. You could do high-level software programming on it. It was available, right? So that was the Sonata program. So Sonata, which is many of you have used and seen, are these boards that run, and our set of RTL that runs on top of that, that includes a sort of a demo system, an FPGA-based demo system that includes a CHERIot IBEX core and a minimal set of peripherals, and an RTOS, and the software on top of that, and all the tooling so that you can create your bit streams and actually run it, right? So Hello World becomes possible in CHERI. We've distributed many of those, and 125 boards have gone out to commercial organizations and to universities, and the board itself, the design of the board itself is open source, right? So if you want to make your own, you want to tweak it, you can. So that was the phase one of the project, and that was successful. As a result of the success of that, well, actually commercial grade DV, interstitial. So we worked with the University of Oxford to formally prove that the CHERI IBEX core complied with its sales specifications. So you have normal DV that you would do, and this is going beyond that sort of functional DV that would normally be available. So this is actually a very high level of security or assurance, rather, that the core does what it says it does on the tin, which is great. So we also then, last year, were founder members, both of us, of the CHERI Alliance. I think this slide is out of date. Every slide that shows all the members of the CHERI Alliance is out of date. There's new people join, so it's a rapidly growing organization. But that, as Mike said earlier, is a place to host working groups, but also to center marketing, and it's a sort of central place to talk about the benefits of CHERI and to drive those processes forward. So we're really happy that that's happened. That's another part of that route to market, and DSIT has helped with that, obviously. Now, phase two, how do you get it into processors? Because that's an FPGA-based thing, and you want to get it actually into processors that are commercially available that people can use. So in phase two, SCI joined the project, which was great. The project was extended, both in terms of time and money. And the goal there was to create a top-level ASIC design. So yes, it has the core in there, but it has a usable set of peripherals. It's a high level of design verification. It's designed to be taped out, right? So as part of that, we have done this Sonata XL board, which is the Sonata board, but it's got a higher, larger gate count FPGA on it. You can plug in sort of daughter cards to it, so there's an Open Titan card that you can plug in, so you can talk to the commercial Open Titan silicon. And there's another one that allows you to plug into the SCI, forthcoming silicon. We'll talk about that in a second. Those will be available from May to order, and they're big enough to be able to run not just a sort of little demo system, but a complete usable microcontroller. So that's sort of one of the outputs, and sort of the less interesting one. The big announcement is that the Sunburst chip repository has been, just this morning, open source. So as of a few minutes ago, it's now available on GitHub, Apache 2 license, fully permissive licensing. It's a complete design for an ASIC that includes the CHERI IBEX core, that formally verified core, but it also includes peripherals that have been taken from Open Titan, the world's most active open source project that is actually the world's first open source silicon to go into commercial production. So you're using commercial quality blocks, open source working as intended, reusing those, putting it together in a top level. It's available now that you can download. And that's going to be used, and Haydn will talk a little bit more about that now, by SCI as the basis for a commercially available microprocessor line called Iceni. And there's a nice animation of that, but I won't bore you with that. So I think the next piece really is to talk about the exploitation of that, so over to Haydn.
Thank you, Gavin. And just getting into this as well, I think, again, just thanks to Innovate UK and DSbD for enabling the funding for this project. It really does substantially help move the ball forward. I think the reality... that way. The reality of the problem is that there's a lot of work on Sonata, there's a lot of work around CHERI in general, but until you can buy it, it's a good academic project. And to, I think, Brad's point earlier, we have to ensure that people can start to actually commercially purchase CHERI. In the conversations that we're having, this is the biggest single barrier to CHERI adoption now. Can I buy it? Can I integrate it into my system? And it's really important that we have a phased approach to this. We are evolving the silicon. We will have initial silicon there in fourth quarter. but we have to move people along the pathway to the final silicon. It takes time, it's incredibly expensive, it's incredibly challenging, but in partnership with lowRISC, in partnership with our back-end integrator, which is Cadence, and in partnership with our foundry partner, which is Global Foundries, we're targeting 22 nanometers for the device. Collectively, we can get it over the line. So obviously, many of you in the room we've been working with around Sonata, around CHERIoT, and around the Sunburst project to enable people to start developing in anger. The next stage to that in second quarter and through the summer is basically to move to the Sonata XL board, the new board that Gavin was talking about, which will enable us to really implement the entire chip. Here's one we made earlier. It does function as well. So we've got some work to do to port both the existing CHERIoT solution, but then also our complete chip IP, which is called Iceni. And the reason for that, as many of you will know, the Iceni was a tribe here in East Anglia, which fought the Romans. Queen Boudica is the most famous Iceni there. And we wanted to take that out and celebrate it around the world as something which is unique to this area, but something which can also drive change around the industry. So we will have the full Iceni chip RTL implemented in Sonata XL later on in the summer. And then from our perspective, we'll also be doing a first tape out late summer. And then we will have silicon back at before the end of the year, providing everything works and is clean. And that's important for us. We have to make sure that we can get that in customers' hands as urgently as possible while still enabling them to do their development. Because of the work that we've done with lowRISC, obviously compiler and debug efforts have moved forward substantially. The compiler work that the team's done collectively, we're actually now on LLVM 19, so we are barely behind the main trunk, and I think very quickly we can step into that as well. Debug, a bit more to do, but we're getting there. So in terms of the roadmap, we are bringing through that initial silicon in 2025. And from our perspective, what that means is, come and tell us what you need. We still have the ability to make some changes. I'll talk about features in a second, but fundamentally we are working with the lead partners today on how we integrate this into systems. A good example of this is a tier 1 industrial electronics company. We talked to them, that number of 50 to 60% of the VP of Cyber's job of his life is memory safety bugs. And of that, 89% is software supply chain. It's killing them. They are a tier 1 company. They produce fantastic software, and yet they pull in their libraries, they pull in their applications, and it sucks badly. And we have to collectively do something about that urgently, and the question is, how do we start to impact that? In terms of the features, subject to change, always put the caveat on that, we are looking at implementing a very broad-based microcontroller, microprocessor application. We feel that in the 22 nanometers we can achieve 300 megahertz. Early devices are going to be very memory rich because we want to be able to do a lot of exploration. As you would expect with microcontrollers, A to Ds, D to As, pulse width modulators, USB 2 host will be on there as well. So we have all of that IP locked in and moving forward, and we're in a good place there, and obviously inherently CHERI orientated. Down the bottom in the system is also what's called a pin mux, which we'll have in the system. And this will allow us to route out the signals to the chips on quite a rich perspective, which will enable us to be pin compatible with a range of existing devices so that the cost of moving, transitioning is reduced. As many of you will know, I originated the Cortex-M cores and other deeply embedded cores at ARM, probably 20 years ago now, my lord. It's very important to understand why they were successful and how we move that forward. And the reality is because they were easy to use. They were written, or they were architected by a software engineer for hardware to implement. And we are looking to do the same again. We want to make sure that we have the right performance points, not only that we hit microcontroller points, but that we can regain the microprocessor application processors and pull them down. As we've talked about before, people are moving to Linux because they want strong thread separation. That's crazy. We can reduce the bill of materials by an order of magnitude by pulling it back into microcontrollers. PinMux drives pin compatibility, and obviously simplified software portability is important. We've proven this collectively, being able to take the C code, do a recompile, and you're going to get a lot of the memory safe capabilities. You may not, automatically get a lot of the compartmentalization goodness that is there, and David Chisnell has done a fantastic book, which probably many of you have read already, and demonstrating how we can bring compartmentalization into the network stack and into applications and move that forward. Final thing at the bottom here, I hate the fact personally that security is seen as an insurance policy. It's a fallacy and it's a backwards way of doing the marketing. The reality is we have to get on our front foot and we have to talk about security as a productivity gain. The ability to reduce costs because we can do faster software development, we can bring in code from GitHub or previous projects and just reuse it and capture the issues and resolve them is a massive productivity gain for the industry. We shouldn't have to have specialists who, it's great if you know Rust, but there's not enough engineers out there who understand Rust, or Ada, unfortunately, or others. We have to work with what we've got. We have to enable better code development. This, in turn, brings faster time to market, better user experience, and, of course, better trust models as well. So in conclusion, and I'll pass back to Gavin here, why is this so important to us? Well, it's really important because if it's just SCI or just CODASIP or just a few of us in this room, we're the idiots. We're the outriders. We're the people trying to change the world on our own. We have to enable a viable ecosystem at scale. And while, we at SCI, we have a lot of differentiating technology around the core. We have to have cores and we have to have software and we have to have mechanisms which are scalable across the globe. So the Sunburst project has been fantastic. It's been a very cost-effective and efficient way of driving this forward. We're very grateful for that and for our partnership with lowRISC as we bring this to market. Any questions around the product and stuff like that, talk to David or Robert or myself out in the foyer. We're happy to sell it to you. Gavin.
Yep, okay, in the last sort of 30 seconds, let me just press stop here so it doesn't beat me. I'm misusing my... No, I'm facilitating the session, right? So Haydn said it very well. So the project, how do you get stuff to market? You need people really making it. You need the fundamental design. And it's our belief at lowRISC that the core of the stack, the core of the design should be open to everyone to use. And we have this morning just made it, open for everyone to use. That doesn't mean, of course, that there isn't differentiated technology in SCI's products. Of course, there is. What it does mean that not just SCI but others, if you want to come and build a microcontroller class core based on CHERI IBEX, you have the tools available and the repo available today to do that. And that's been an output, really an important one, or the most important one, as well as the boards and all the other pre-RTL of the Sonata project. So we're very thankful for that, for the UKRI and the Digital Security by Design program, and of course to Microsoft and others. And going back, the whole lineage of this, University of Cambridge, University of Oxford, it's been a huge collaboration between academics and industry and government, and it's now seeing real products coming to market. So that's the announcement after this. Go download the repo, have a look at it, and it'll be growing and active. We hope as active as the Open Titan one was, which is...
Or buy the product.
Or buy the product, or both. Or both. Thanks very much. Thank you.